John is given two sunflower plants. One plant is 16 centimeters high and the other is 24 centimeters high. John measures the height of each plant at the same time every day for a week. He notes that the 16 centimeter plant grows by 4 centimeters each day and the 24 centimeter plant grows by 3.5 centimeters each day. So here is a table, and we're looking at the heights of each plant for 7 days of a week. So in green we have the heights of one of the plants. That is the plant whose initial height is 16 centimeters. So on day one its height is 16 centimeters. It grows by 4 centimeters each day. So we just add 4 on to its height each day to get its height on the next day. The 24 centimeter plant grows by 3.5 centimeters each day, so its height on day 1 is 24, and we just add 3.5 onto 24 to get its height on day 2. That gives us 27.5. Adding 3.5 onto the 27.5 gives the height of the plant on day 3, and so on. Write down two formulas, one for each plant, to represent the plant's heights on any given day. State clearly the meaning of any letters used in your formulas. Now we could actually do this in two ways. One way is to think of the height of each plant as being an arithmetic sequence. You see here, say for plant 1, the first term is 16, the second term is 16 plus 4, which is 20, the third term is 20 plus 4, which is 24, and so on. So we could do it like that. The same is true for the second plant. For the second plant, the difference is actually 3.5. So this is one way we could do it. So I would just do it this way now, and I will do it a different way soon. So we're interested in finding a formula for this sequence here. So I'm going to start with the height of plant 1. The first term T1 is 16, the second term is T2 is 20, and so on. We're interested in a general term for this sequence, that is the nth term, Tn. Now, in previous videos, you saw that Tn for an arithmetic sequence is given by a plus n minus 1 times d, where a is the first term. The first term in this sequence is 16, and d is known as the common difference, got by taking any term and subtracting the previous term. 20 minus 16 is 4. We know that was given in the question. This plant grows by 4 centimeters each day. So what we have here is 16 plus 4n minus 4. I'll write the n term first, 4n. 16 minus 4 is 12. So this is a formula that will give us the height of plant 1 for each of the 7 days of the week. So for example, if we plug 7 in for n, we get 4 times 7 is 28. 28 plus 12 is 40. So the height of plant 1 on day 7 is 40 centimeters. Now a more meaningful way to write down 4n plus 12 is to change the letter n to say the letter d, where d stands for day, and Tn, the nth term of an arithmetic sequence, is replaced with h1, h being the height of the plant. So h1 is the height of plant 1. You could also look at this as the equation of a straight line, which I will get to soon. You know, this is the equation y equals 4x plus 12, where x is the day, y is the height, and we could actually draw this line. Now we do exactly the same for the height of the other plant. That's also an arithmetic sequence. The first term is 24, the difference d is 3.5. So to get the nth term, we have Tn equals a plus n minus 1d. A here is 24 plus n minus 1 times d is 3.5. So we get 3.5n, and we have plus 24 minus 3.5. What's that? That's 20.5, I think. Actually, it's 21.5. I'm sorry, it's 20.5, of course. You can see that this checks out, say, by plugging in n equals 2. If you plug in n equals 2, we have 3.5 times 2 is 7, 7 plus 20.5 is 27.5, so we get the second term. So it checks out for n equals 2. It's actually true for all values of n. So we could write this as h2 being the height of the second plant, equals 3.5 times d, where d is the number, the day. D runs from 1 to 7 actually, plus 20.5. So we could write it like this. It's just easier to read. You could also think of this as the equation of a straight line, which we can graph. It's an equation with that is y equals 3.5x plus 20.5. We could actually graph both of these straight lines on graph paper. Another way we could get these lines is to pick 2 points, say for plant 1. It's a fact that the graph for the height of plant 1 is a straight line, it's linear. And we can get the equation of that straight line by considering 2 points on it. So if the horizontal or x value for the graph is the day number and the y vertical value is the height of plant 1, then we could pick, say, the points 1, 16 and 2, 20 and get the equation of the line passing through those 2 points. The line passing through these 2 points will also pass through the points 3, 24, 4, 28 and so on, because the height increases linearly with time. We're just adding the same amount on. So the equation is actually a straight line. So to get the equation of a straight line, we could first get the slope of the line by y2 minus y1 over x2 minus x1. That's equal to 4 over 1, which is 4. Then we can get the equation of the line, which is y minus y1. I put 16 in for y1, equals m, which is 4, times x minus x1. x1 is 1. So then this would lead us to y equals 4 times x minus 4, add on to 16, minus 4 plus 16 is plus 12. So we can get this equation here. So this is another way that we could do it, using coordinate geometry of the line. Of course, this is only true if the plant's height varies linearly with time. That means that for equal increments of time, the height increases by a fixed amount, 4 centimeters in this case. In this graph, I show the heights of the 2 plants over the first 4 weeks. 4 weeks is 28 days. Now, in order to fit this in here, I have different scales here. Each of these ticks represents 1 day, and here I'm going up in steps of 10 centimeters. So for the first plant, at day 1 the height is 16. So if we go to 1 and up to 16, we have this point. And at day 7 the height is 40. So if we go to 7 and up to 40, we can plot 2 points and then draw a line. And we want to show the growth over 28 days. So it's assumed here that the plants will continue to grow at the same rate. So that means for the first plant, it will continue to grow at a rate of 4 centimeters per day. And for the second plant, it's assumed that it will continue to grow at a rate of 3.5 centimeters per day for 4 weeks. If that is the case, the graphs will be straight lines over 28 days. So if we pick a point on this line here, which represents the growth of the first plant, any point at all, and increase x, or t if you like, for time by 1 unit, then y, which is the height, will increase by 4 centimeters. So no matter where you are on this green line, pick any point, increase x by 1, then you will have to increase y by 4 to meet the line. So the slope of this line is 4 over 1, which is 4. This number here, the coefficient of x. We get something similar for the other line. If the growth is constant for the second plant over 4 weeks, then if we pick any point on this second line, increase x by 1, y will increase by a fixed amount. It will increase by 3.5. So the slope of this line is 3.5. I have decided to use Y to stand for the height and X to stand for the time. Although you could use one of these. You could say the height is 4D plus 12 for the first plant, and H equals 3.5D plus 20.5 for the second plant, if you like. Now in part D, we want to use the diagram to write down the point of intersection of the two graphs. Now, I've cheated a little bit here. I actually worked out the point of intersection earlier. It's actually this point here. So if we read down here, this value of X is 17 and the value of Y is 80. The meaning of the point of intersection is the time at which both plants have the same height. So after 17 days, both plants will have the same height of 80 centimeters. Now, when you do this, you mightn't exactly get 1780 because I worked it out in advance. But if you take this point, it should roughly satisfy the equations of both lines. So if we take this line here, which is the equation of the growth for the second plant, and we plug in 17 for X, and we should get out 80 for Y. So I plug 17 in for X in the equation of this line, and if you work all of this out, we should get 80. Now you might not get exactly 80 because you might have read off this point as, say, at a time of, say, 16 days or maybe 18, but you should get close enough to the Y value, whatever it is. It won't be 80 unless you do it precisely. It should hopefully be close to 80. If you plug 17 in for X in the second equation and work this out, you'll get exactly 80. Both of these numbers are the same. So if you get the precise point, then the Y values you get out will be the same. But if you're close to it, you should get two Y values that are pretty close. If you want to work it out algebraically, what you do is you solve between this equation and this equation here. The easiest way to solve between these two equations is to equate the right hand sides. Put 4x plus 12 equal to 3.5x plus 20.5. You can do that because the right hand sides are both equal to the same thing. They're both equal to y. So if they're both equal to y, they must be equal to each other. If we solve this equation, we have 4x minus 3.5x is 0.5x. On the right hand side, we have 20.5 minus 12 is 8.5. You can divide 8.5 by 0.5 to get 17, or if you like, you could multiply both sides by 2. 2 times 0.5 is 1, 2 times 8.5 is 17. Knowing what x is, we just sub this value back into one of these equations and we can get y. So if we sub it into, say, this equation here, we get y equals 4 times 17 plus 12, which equals 80. Of course, the advantage of finding the point of intersection by algebra is that we get the precise point of intersection, whereas using the graph depends on how accurately we've drawn the graph. If John is correct about his assumption that the plants will continue to grow at the same rates, that is, the graphs are lines, straight lines, then if he observes the plants to have a height of 80 after 17 days, he knows that he's got a good model. However, there's no guarantee that the plants are going to keep growing at the same rates. It's not guaranteed. They might do so for the first 7 days. It's quite possible that the graph for the height of the second plant might do something different, or might not follow a line, might follow some sort of a curve. It's quite possible that the growth rate might slow down. Plants obviously don't keep growing at the same rate forever. Otherwise, plants would never reach a maximum height. So there must come a time when the growth rate of a plant slows down, so its height reaches some maximum value. If we just assume that the growth rates are linear, well, a line could continue on indefinitely. Of course, something similar could happen for the first plant. So if the graphs are not linear beyond a certain time, say beyond 7 days, then the points of intersection could be very different. The plants could reach the same height after fewer days than 17, and that height could be considerably less than 80. Of course, John could be right in his assumption that the plants grow at the same rates for 4 weeks, but at some stage the growth rate will have to level off. Plants can't keep growing at the same rate indefinitely. So at some time in the future, if not within 4 weeks, then the graphs will become curves that level off to a maximum height. So both plants will reach some maximum height at some stage. If not within 28 days, then sometime after 28 days.